Hi. Now that we have finished all our repetition of basic functions that you had in high school, the next thing we need to repeat is logics. We're going to just tackle with basics of logics because we need to use a lot of logical symbols in our future lectures, but this is something we definitely need to do. Okay, and we're going to start, of course, from basics. So first, logical statement is a statement that can be either true, which in logics we denote as 1, or false, which in logics we denote as 0. So look, in other words, a statement is the type of sentence where we can assign a logical value 1 or 0. So it means that this statement will be either true or false. Okay, this is not something very complicated, but let's illustrate it with an example. If I'm going to say, I'm in the classroom, this is a logical statement. Why? Because I actually am in the classroom, well, at the time of the recording. So we can say that this is, what I'm saying is true. So this is a logical statement. But even if I would say, I'm not in the classroom at the time of this recording, it still would be a logical statement. Why? Well, because we can see that I am in the classroom, so we can easily assign logical value of 0. So we can say that this statement is false. But, so is every sentence a logical sentence? No. Look, if I'm gonna say, do you want to go for a beer? Well, this is not a statement, this is a question. I cannot tell if this is true or false. So this is not a logical statement. Now, something a little bit more controversial. God exists. Well, probably different people would assign different value to it. Probably believers would assign, based on their belief, value 1, while atheists would assign, would say that this is a false statement, and logical value would be 0. But actually, this is not a logical statement. Why? Because nobody has proven that God either exists or that God does not exist. So we cannot say. And if we cannot assign logical value, either as something is true or not, this is not a logical statement. Okay, and those logical statements we will be denoting with lowercase letters P, Q, and R. Those will be very short in our usage, and we will be combining them into bigger statements using logical operators, and we will review just the 5 most basic ones. So, the first one looks like that, and we call it negation. And we read it as not. Then we've got conjunction, and we read it as and. Then we've got disjunction, we read it as or. Well, alternative name for disjunction, alternative. So we can use it interchangeably. Then, if we see an arrow pointing to the right, we call this implication. And we read it as if something something, usually we put some statement P, then something something, usually we'll denote as some statement Q. Okay, and finally, if we have arrows pointing in both directions, we've got biconditional. The other names for biconditional are by implication or equalization, and we read it as something something, usually some P, if and only if something something, usually Q. Okay, so now we can check how they work. When we check how they work, we use something called propositional calculus. Okay, so what is propositional calculus? Well, it's in the simplest form, we can say is using a table to check something's logical value, just like we did in high school. So, if for example, I want to check negation, negation involves just one statement. Let's just say it's P. P can be either truthful or false, right? So, not P will be either, it will be false if P is truthful, and truthful if P is false. Well, very easy. Now, all other symbols that you see over here involve at least two statements. So now we need to use two statements. And look, in this case, those statements will be either both true, only the first one will be true, only the second one will be true, or they both can be false. So we have as many as 4 different combinations of their logical values. Okay, so now let's go through all the possibilities over here. Let's start with conjunction and disjunction, because they are actually very closely related. Especially that when we use and or in common time, we do it inappropriately. And if we are doing it inappropriately, we do not get the precise meaning. And this is what we're going to establish today. Look, conjunction, when we have and, means that both conditions must be fulfilled. On the other hand, with disjunction, only one condition needs to be fulfilled. So, in this case, it means that if there's and, we require both of the substatements to be truthful in order for the full statement to be a true. On the other hand, in case of disjunction, only one, at least one needs to be truthful for the entire statement to be truthful. Okay, so here we've got that if both are truthful, here we will have one because they are both truthful. But look, over here at least one is false everywhere, so we will have 0, 0, 0. Here on the other hand, we require just one to be truthful for the entire statement to be truthful. So we've got 1, 1, 1, 0. Okay, then we've got implication. And when we talk about implication, if something, if P is truthful, then Q, and again we get truthful, the entire statement must be truthful. Now the problems are starting to appear a little bit later. Okay, now, if something truthful implies something false, well, clearly the entire statement must be false. Now, let's go to the bottom. If something false implies something false, the entire statement is truthful because one falsehood leads to the other. And finally, this one is usually the most to comprehend, but actually as you will be studying economics for a long time, you will see that this one is the most important for an economist. If something is false but implies something that is truthful, then the entire statement is truthful. Why is it so important in economics? Because look, in economics we cannot make experiments. We usually need to build mathematical models to explain the reality. Mathematical models are simplifications of the reality. So we know that they definitely need to be false, but they give correct predictions of what is going to happen. And so this is the case that we have in economics actually the most often. Okay, and finally, biconditional. This one is also very simple. Look, biconditional requires for the logical values on both sides of the statement to be truthful, to be the same. Logical value on both sides must be the same. Then the statement is truthful. So look, if they are both truthful or they are both false, we will get a truthful statement. Now, if they have different logical values, so one of them is false, one of them is truthful, then we've got a false statement. Okay, so this wasn't that complicated, I hope, but let's now see how we can use what we've learned on some examples. Okay, and let's start with this. If the moon is green, then Warsaw is the capital of Poland. Okay, so what do we see over here? We clearly see that we have implication then, and we have two statements. Let's call the first one P. Now, is the moon green? Well, we cannot say with certainty, probably just looking from Earth, but definitely the scientists from NASA have proven beyond reasonable doubt that the moon is not green. So we've got 0 over here as a logical value of this part of the sentence. Then we have sorry, where are my colors? Oh, here. Now this part, let's call it Q, is Warsaw is the capital of Poland. Well, this statement is definitely truthful. So look, I can write this entire sentence basically as P implies Q. And now, if something false implies something truthful, well, this entire statement, though very weird, is a true statement in logical sense. Okay, let's try now something different. What if I reverse the order here? So now if I have F Warsaw is the capital of Poland, then the moon is green. simplification, this is our first statement. This statement, let's denote it as P, we already established, is truthful. Now, the second part, let's call this now Q. This part is false. So look, we've got a situation when something truthful implies something false. So entire statement must be false. Okay, now let's complicate things slightly. So now we've got, if Warsaw is the capital of Poland, and water is dry, then the moon is green. Now, look, first thing we should notice is that our sentence got slightly more complicated. Now we can divide it into three sub-statements. So, we got Warsaw is the capital of Poland. Let's denote it by P. And we know that P is a truthful statement. Now, whether water is dry, well, dry water is a popular oxymoron. And so we can clearly be sure that this one is definitely false. Let's denote it as P. Okay, now finally the third statement. The moon is green. Let's denote it by R. We know that this is a false statement. Okay, now look, let's consider this step by step. We have Warsaw is the capital of Poland and water is dry. Right? We need to consider those two first. So P and Q. Now look, if we have conjunction and, this means that both of them need to be truthful for the entire statement to be truthful. So we see that the logical value of this is 0. Now, if we have we can write this entire sentence in the form of P and Q implies R. Now, we know that P and Q is 0, R is 0. Now, if something false implies something false, the entire statement is a true statement. Even though the sentence is very weird, does not bring much to the table in terms of informational content, maybe except for the P part, this statement is true. Okay, now let me just change something slightly here. What if I would put or over here? Well, this would change a lot. Look, because if we got or, so if I have alternative disjunction, I would have here or. And now look, in case of or, only one of the statements needs to be truthful for the entire statement to be truthful. Now, in this case, the statement can be expressed as this. And we see that it has a logical value of 1. But if something truthful implies something false, the entire statement is false. Okay, I think these examples actually explain very well the basics of how we can assess logical value of a sentence. Now let's move to another thing that is called tautologies. So, tautology is a statement that the logical value of tautology is always 1. Look, mathematics is actually very often called reproduction of tautologies. What does it mean? Look, in mathematics, we have axioms. Axioms are the truth that we cannot prove, but are so obvious that do not require to be proven. Although, you know, some people might argue about it. Then, from this basic truth, we are deducing everything else. And look, when we do so, we have the requirement that left-hand side and right-hand side are always equal to one another. This is why generally mathematics can be thought of as the science about truth and is involved in the reproduction of tautologies. Okay, so now that we know what is a tautology, let's see a couple of tautologies. Okay, we're going to start with very simple. We're going to start with very simple tautologies, and we will be proving them. Not all of them, but I just want you to see, because there will be different levels of complication in those tautologies. So we will require more complex tables, basically, because we will be proving them using propositional calculus. Okay, so what are our tautologies? For example, P or not P. I don't think we even have to prove it. Look, if something is true, P can be either 1 or 0, right? So if P is 1, not P is 0. If P is 0, not P is 1. Alternative requires the 1 to be true for the entire statement to be truthful. So even without like a formal proof, we can see that this statement must be a tautological statement. But okay, let's first write down a couple of them, like law of contradiction. And in the case of the law of contradiction, we've got not P and not P. Then we will have law of double negation. So we've got not P is the same as P. Again, we will prove this. It's one of them. But we will do it anyway. Now, let me introduce just 2 more laws. First one basically states that negation of conjunction is alternative of negations. And the next one says that negation of an alternative or disjunction is a conjunction of negations. And those 2 laws are called De Morgan's laws. Okay, so maybe let's start by proving law number 3. So how do we do it? We use the propositional calculus, so we use the table that we've used previously. So if we've got P can take 2 values, 1, 0, right? Then we will go from less complex statements to a more and more complex statement. So look, in this case, the next one we would like to do is not P. Not P is, if P is truthful, then not P. So look, we simply negate now whatever we've got here. So if not P is false, this is true, this is false. And look, what we will have over here now, is that we need to check, because we've got biconditional, if the logical value over here and over here are always the same. So we can write this is not P, so the full statement, if and only if P, and we see the same logical value, This is a tautology. Okay, so now let's maybe try to prove let's just say the first one of the De Morgan's laws. Or maybe the second one, because I need more space on the whiteboard, probably to do it. Okay, so, look, when we prove a statement that involves two substatements, we write it as P, Q. And look, here we have four different possibilities. 1, 1, 1, 0, 0, 1, 0, 0. Okay, so here we see that we need to start with P or Q. So, P or Q. Now, at least one of them needs to be truthful for the entire statement to be truthful. So we've got 1, 1, 1, 0. Then, we've got this entire statement. We need to negate what we've got over here, right? So we just change the logical value in the previous column to the opposite. And look, now, because look, those tables are usually getting pretty big, the good thing to do is to say that this will be called left-hand side of the biconditional. Okay, now, what else do we need to do? We need to deal with the right-hand side, but also we're going to start with very simple statements. So now we need to deal with not P, so we can have either 0, 0, 1, 1, and not Q. Not Q gives us 0, 1, 0, 1. And then finally we can put them together, that's not P and not Q. Now, for this statement to be truthful, both of them need to be truthful at the same time. So we've got 0, 0, 0, 1. And let's call this part the right-hand side. Okay, so when we have the right-hand side, we can now do whether left-hand side is the same logical value as the right-hand side. So now we will be looking only at those two and check if they have the same logical values. 2 zeros, 1. 1, 1, 1. Again, you see, doesn't matter what is the logical value of P and Q in this statement, we will always come up with the truth at the very end. Okay, now let's make things slightly more complicated. And let's introduce 3 more statements. P and Q or R is the same as P and Q or P and R. Right, then we've got that P or Q and R is the same as P or Q and P or R. Oh, and maybe just one more. We've got that if P implies Q and if Q implies R, then P Now, again, I'm going to prove one of those statements, and at home, please solve and prove all other tautologies. Plus, of course, in the exercise set I've prepared for you, you will find more of those tautologies, and you can also practice by proving. Okay, let's start with the first one. Okay, now the situation is a little bit more complicated because we have three statements: P, Q, and R. So we should have 8 possible cases of them. And so we can have either 1, 1, 1, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0. I recommend this order because it makes perfect sense, because we always start to put one logical value 1 on the first statement, but look, technically it doesn't matter, it's just really nice organized. Okay, so again, we need to start by making more and more complex statements. So here first we need to do Q or R. Okay, so we just need to look here. If both are true, if at least one is truthful, the entire statement is true. So we've got 1, 1, 1, 1, 0, 1, 1, 0. Okay, then we've got P and Q or R. Okay. So now look, all I need to do is to look at those, and they both need to be truthful for the entire statement to be truthful. So I've got 1, 1, 1, 0, 0, 0, 0, 0. And again, this is going to be our left-hand side. Now we're just going to move to the right-hand side. On the right-hand side, we start with P and Q. So I'm just looking at those. Both need to be truthful at the same time. 1, 1, 0, 0, 0, 0, 0, 0. Okay. Then I have P and R. And now I look at those. I got 1, 0, 1, 0, 0, 0, 0, 0. And now I need to make an alternative out of those two. So here I will have P and Q, or P and R. And now I just look at those two columns. So I've got 1, 1, 1, 0, 0, 0, 0, 0. And now we can call this the right-hand side. So now we need to check if logical values on the left-hand side and the right-hand side are the same. So if I do so, if I just check 1, 1, 1, and then look, I've got 0, 0, 0, 0, 0. So 1, 1, 1, 1, 1. We see again, doesn't matter what we put instead of P, Q, and R, as long as they are logical statements, but regardless of whether they are true or false, and we will always have a truthful statement. Okay, the one last thing we need to do about logics are quantifiers. Okay. So first, we will have universal quantifier. Universal quantifier, we write it as this, and we read it as for every. And the second quantifier is called existential. Quantifier. And we write it as like backwards letter E, and we read it as there exists. There exists. Okay, now let me show you a couple of examples how they work, and we will see. We will assess their logical statements. Okay. So we start with this. So here we have some group that we are concerned with, and here we have some statement for which we use this quantifier. So look, here we've got for every x, x is equal to x. Well, that is definitely a truthful statement, right? But what if we have a different statement? Like, for every x, we had square root of x squared is equal to x. This one doesn't look right. Why? Because, for example, if I'm going to take negative 1 to the power of 2, I'm going to get 1. If I'm going to take square out of this, I'm going to get 1. So we see that there's 0. But maybe we can respond to this more formally using existential quantifier. And there exists, right? Why this is false? Because there exists such x squared, such root of x squared, that this is different than x, right? Our example was negative 1. But of course, so this is a true statement, because now we could also simply write that there exists such x squared, square root of x squared that is equal to x, because of course we can also find example. Here the example would be just 1. Okay, now maybe okay, 2 more examples that we've got is that for every x, x squared equals to x. Of course, this is false because example would be 2. But we still can say that there exists such x that x squared is equal to x, and this is truthful. For example, 0 or 1. Okay, and the one last thing I promise about logics are the 2 laws associated with quantifiers. And look, they make perfect sense. So not for every x, y. So look, we read this as for every x, some statement y. If we say that this is not truthful, this is the same as saying that there exists such x that not y. Okay, and our final law is about negation of existential quantifier. If there not exists such x then y, this is the same as saying that for every x, not y. Okay, and this is everything set theory, we will also be concerned with just basics, but I will already use some of the stuff that we've learned in this video. Okay, take care and see you in the next video.